Hello there guys, Teacher Krishna here, and welcome to our next class for the third unit. This is a class that is part of Big Hive School, of course, and it will be part as well of 10th High School. Just like you know, this is our lesson for physics, and we are going to be working on week number 22. So I'm pretty sure that you noticed that I'm not in the video one more time, but a little bit of a spoiler for today. And the lesson is going to be a little bit longer than 15 minutes. And unfortunately, the program that I used for recording myself last time only allows me to record for 15 minutes. But don't worry, we still have the presentation, and I'm going to be helping you out in case you need anything else. So let's go over our presentation for today. Very important, remember to have your notebook with you in order to make today's summary. These are the parts that you need to include in your summary. Include the date, ending mind, title, summary of course, and some extra decoration. It is very important to remember that each one of these parts is going to include a certain color pattern. Remember, ending mind and title must have red and blue, and the rest of the summary must be written down with red and black. Make sure to have these materials with you before starting, and when you are ready, you can continue with the video. Alright, so today we are going to be studying topic 3.01, Newton's first law. And in the following weeks, we are going to be working in the rest of the Newton's law. We're going to study the second law and, of course, Newton's third law. Each one of these laws are very interesting, and of course, we're going to be doing some great experiments that are going to help you out to understand the topic a little bit better. And of course, it will let you know the way these laws can be applied in a real-life situation. Okay, so what is the ending mind for today? The students will be able to understand and describe Newton's first law by completing several application, theoretical, and physics problems. Make sure to keep track of the ending mind in your summary. And once again, when you are done, we can continue with the video. Alright, I'm going to give you a small summary of the activities that you need to complete today. Number 1, watch this video and make a summary. Of course, this is the activity that you are already doing. Number 2, read topic 3.01 and complement your summary. I included most of the information from the topic, but it is always necessary to reinforce your reading skills so you can take a look at the content one more time and of course learn everything a little bit better. Number 3, complete the remaining application exercises in page 3 from topic 3.01. So in this presentation, I'm going to be showing and explaining several application problems that are found in topic 3.01. But there is a specific part in page 3 for students to practice all of the knowledge that they have acquired. So when you finish with the video and all of the explanation that we have here, make sure you remember to go to page number 3 and complete the exercises from there. Lastly, number 4, complete the assessment for topic 3.01. After this video, after you have read already the topic and completed the exercises, I'm pretty sure that you are not going to have any sort of problems for completing the assessment for today. Alright, so let's go over the topic. So who is this guy that we have right here? Well, that's Newton actually. And because of the topic is Newton's first law, he was included as part of the presentation right here. So let's analyze a little bit about him. So Isaac Newton is known as the father of classical physics. And when he was 23, he developed the law of motion, complementing the Aristotle's theories. So Aristotle is a very remarkable person in history because many of his theories and many of his thoughts were used in many historical places, and they were taken as the absolute truth. But after Isaac Newton discovered these laws, then the laws that were previously created or stated by Aristotle were changed a little bit. And here is why. Well, Newton's laws describe the relationship between force and motion. They do not describe why those forces act in such a way. They only describe their behavior. So this is something very important and something extremely interesting to analyze about a law. So Isaac Newton started describing the behavior of the objects in different situations. And what you need to know about a law is that it is something universal. So it doesn't matter in what part of the universe you are at, then this law cannot be changed. That's something astonishing, right? So that's part of the first law that Newton created. And here's something very important that we need to distinguish in between a theory and law. So what is a theory and what is a law? So first of all, let's read the definition for theory that we find right here. So theory, the credibility or authenticity of theory depends on the amount of evidence that supports the theory. So, for example, here is Darwin's theory of evolution. So this theory usually it has a great conflict with religion and also the creational theory, because just like it says, it depends a lot on how much evidence you have. And for many people, for many religious people, us humans and the whole universe was created by God. But that is not a law, that is a theory. And some other people that believe in the theory of evolution, they believe that the monkey was once one of the forerunners of humans. So notice that the theory can change with time. So let's suppose that another theory comes out that has way more evidence than the theory of evolution, so it will actually take over the previous theory. But this is of course totally different from what a law is. So what is a law? A law is an established, universally observable, solid fact. No further evidences are required to make it more authentic. So what happens is like just what I mentioned before, like no matter in what part of the universe you are at, no matter if you are here on Earth or if you are in the moon or if you are, I don't know, out of this galaxy, that specific law is going to be applied in there. All right, so notice that laws cannot change because they are universal, so they cannot change at any time. And that is exactly why Isaac Newton was such a remarkable character in history, because he discovered one of these principles that are applied absolutely everywhere. Now we need to take a look at some key concepts. So Newton's first law of motion. A force is needed to change the motion of an object. So if an object already has motion, or if an object is already stated at a certain place, it needs another force in order to change its state. And it follows two simple principles. The first one, an object in rest will remain in rest unless an unbalanced force affects it. So that will be the first one. And how about the second? An object in motion will remain in motion unless a force acts on it. And for these concepts, we also need to analyze the concept of inertia. What is it? So it is an object's resistance to change its motion. The higher the mass of the object, the higher the force needs to be to affect its motion. Also, we have some important aspects to consider. So when a car stops, your body still moves. So your body resists to change the speed that was previously added to it. And lastly, we have how do you get ketchup out of the bottle when it resists? So here's a person, of course, taking ketchup out of a bottle. But if that has ever happened to you, when ketchup just stays at the bottom of the container and it doesn't want to go out, well, then you're going to shake it. And you are going to be shaking it in such a way in which you are going to impulse the ketchup from the bottom of the container in order for it to actually move. So once you have applied this certain force or this certain motion to the container with the ketchup inside, then all of the velocity that it already has is going to be applied downwards, just like in this case in which it's being served on a piece of bread. So when you drastically stop the bottle, then the motion that the ketchup had is going to continue its, let's say, with its velocity and its direction. So that is basically what is going to happen, and it is going to help you out to take ketchup out of the bottle. And of course, it is related to inertia, because if the liquid or the ketchup had already a force applied, when you stop the bottle, then it is going to resist to that drastic change. That's why it is going to continue with its motion. All right, so let's continue. All right, so now we have some application problems. So how can we apply all of the things that we have learned already? Of course, besides what I have already told you about the ketchup and the bottle. Well, here I have some small questions and of course a couple of explanations for you as well. These are questions that we find in the platform that I'm going to help you out with. So you can have a clear example of everything in here. Let's go with question number 1. So Aristotle incorrectly thought that a moving object must have a continuous force exerted on it to keep it moving. On the other hand, Galileo and Newton thought that in the absence of a net force, a moving object will continue to move. Alright, so now consider a ball rolling across a smooth floor. So number 1, how will Aristotle explain the ball's behavior? So basically, Aristotle will explain that the ball is moving on the floor because we previously applied a force to it. Like if you roll it with your hand, then that is the force that Aristotle was talking about. But in this case, if we want the ball to continue moving, we need to keep on applying different forces to that ball. And let's go with question number 2. How will Galileo and Newton explain the ball's behavior? So remember that Newton explained that unless there is another force that is higher than the previous force that was applied to an object, then it is going to continue moving. So Newton and Galileo will probably explain the behavior of the ball in such a way in which they will say that if you apply a certain force at first to the ball and it is moving already. If there is no other force that affects its behavior, then it is going to continue rolling out. Let's go with question number 3. How will you explain the ball's behavior? So this is something very personal, but I will explain that the ball is basically an object that is, of course, an object that is very influenceable by other energy forces, such as the one that we can apply to it. And of course, depending on what part of the universe we are at, the ball is going to change its behavior. Like, let's say that we apply a certain force to the ball on Earth. What we are going to notice is that at some point the ball is going to stop. But why does that happen? Well, it is going to stop because of basically two forces. The first one that we can mention is gravity, that is always pulling any of the objects to the center of our planet. And the other one can be a friction, that of course is like, let's say, like a force that is acting in the opposite way of the ball's behavior. That'll be on Earth. But if we go to space, what happens if we analyze the force that we apply to it? Unless the ball encounters like another physical space, such as an asteroid or the gravitational pull of a planet, it is going to continue moving because there is nothing that will stop it. All right, so that'll be the question number 1. Let's go with question number 2 right over here. It says place a 3x5 card over the opening of a glass. Place a penny on the 3x5 card. We have a picture that represents its model, and it says flick the 3x5 card. So, the number 1, what happens to the penny? So, if you slowly move the card, then nothing is going to happen to the penny. It will stay in the same place at the top of the card. And number 2, how do you think Newton will interpret the penny's motion? So Newton will argue that if we move it slowly, then it will be following the first Newton's law, because there is not a force that is higher than the force or the inertia that the penny has already in the state of rest. But if we move the card extremely fast, then of course the penny is going to fall from the card, which of course one more time will be related to his theory, because with a higher force it will actually affect the state of rest that the coin previously had. Alright, this is question number 3. I don't know why I didn't put question number 3 at the top, but anyway. It says, think back to the penny and glass demonstration. Number 1, use Newton's first law ideas to explain why the penny rested motionless on the 3x5 card. Well, it's what I was telling you. If you do it slow, it is not going to affect the state of rest of the penny. Number 2, use Newton's first law ideas to explain why the penny fell into the glass when the card was flicked. So, pretty much, if you do it super quickly, it is going to come inside the glass, because we actually have a force that will affect the state of rest of the penny. Okay, so we're going to continue with polys. So for this, we need to analyze what mass is. So mass is the amount of atoms of an object. And of course, it is expressed in kilograms. So this is something very important to take into account. We need to compare it with weight. What is the difference between mass and weight? Because people and students usually confuse both terms. So weight, it is related to the location of the object. It is the interaction of the mass of the object and the gravitational pull of the place where it is at. It is expressed in newtons, because we're studying the Newton's law, right? So, in order to find the weight, we are going to be using the following formula, in which weight will equal mass times gravity. So, notice that the mass of an object is not going to change. Like, if you put the mass on Earth, of a ball, let's say, and you put that same mass of the ball on the moon, then nothing is going to change. What is actually going to change is the weight, because remember that the weight, of course, is going to be taken into consideration the mass of the object as well as the gravitational pull of where it is at. So, of course, usually we're going to be applying the gravitational pull of Earth, and gravity on Earth equals 9.8 meters per second square. Or if we want to write it down in another system of measurement, we are going to have that it will be 32 feet per second square. This is an extremely important number to take into account, because we are going to be applying it a lot in upcoming problems. So make sure to have it in your notebook. Alright, so now let's go with some other application problems related to the second part of this presentation. Alright, this is the first one. It says, little Nilly Newton wishes to be a gymnast and hangs from a variety of positions as shown. Since she is not accelerating, the net force on her is 0. This means the upward pull of the ropes equals the downward pull of gravity. She weighs 300 newtons. Show the scale reading for each case. Alright, so basically the most important information that we need to remember is that she weighs 300 newtons. Okay. So now, this is another principle of physics that we need to analyze, but the tension on a rope is going to be equal to the bob that is hanging from it. The bob is basically the object, or like the person or thing that is hanging from the rope. It's a weird name, but we're going to learn about it later on. So if the tension on the rope is the same as the object, or in this case as Nelly, it will be 300 newtons, because it'll be just basically the same weight. But now take a look at this. Now we're going to be observing two different, let's say, parts from where she is hanging. So in this case, since we have two parts, it is going to be exactly the same, because like it follows the same line in the same tension on the rope. So in this part, the tension is going to be 3 newtons, and in this part, 300 newtons, I mean, and in this part, it is still going to be 300 newtons because it has the same tension. But now, how about here? What's going to happen in here? Notice that the weight is going to be divided in two, because in this case, we have two parts from where she is hanging. And of course, since she's right in the middle of both parts, the amount of weight, it has to be divided by 2. So in this case, on the rope that we have on our left, is going to be 150 newtons. And in this case, on the right, we're going to be having 150 newtons as well. Alright, so now let's go pretty quickly over this one right here. Now we have 3, she is right in the middle, so the weight is divided by 3. So in each one of the ropes we're going to have 100. Now in this case, she is still hanging from the same rope, so it will be 300. And right over here we have that the rope is sticking from one side, then it follows a certain system, and then she is hanging from here. Well, the tension is going to remain the same because it is part of the same rope. And since she is right over here, the result will be 300 newtons. Alright, so now let's continue. And this is number 2. It says, when Burl the painter stands in the exact middle of his staging, the left scale reads 500 newtons. Feel in the reading on the right scale. The total weight of Burl and staging must be newtons. Alright, so this is related to what we were talking about in the previous problem. So notice that he is standing right in the middle, which means that the tension or the weight of the person is going to be divided equally on both sides. So if it is 500 newtons on the left, it has to be 500 newtons on the right. That'll be the result for this problem. Alright, in a silly mood, Burl dangles from the right end. Fail in the reading on the right scale. So remember that he was 1000 newtons. And if the tension on the left rope is 0 newtons, by logic we are going to assume that all of the weight of this person is going to be fully tensioned on this rope. So it means that the weight or the tension of the rope will equal 1000 newtons. Oh, and this will be the end of the presentation. So thank you a lot, guys, for coming. I know it was a little bit of a long topic to explain today, but trust me, it is very simple to apply as long as you have understood already the basics of the topic, and of course you have kept track of the formulas and everything from this presentation. So remember to go to the activities section that I had as an introduction for today, so you can remember a little bit about all the activities that you need to complete. That's it for today. I will be seeing you around during the mid session. It's always great to see you, and always take care of you guys. Goodbye.